Magnetic sensors are a lot smarter than they used to be, and these sensors are everywhere. There's dozens of them in modern vehicles, and even my e-bike has one right down here. In the analog days, this tech was mostly limited to simple edge and frequency detection, but today's magnetic speed sensors have built-in algorithmic processing to deduce things like direction and position, and to overcome environmental challenges like temperature drift and air gap changes. So in today's Tech Chat, sponsored by Mouser Electronics, I'm joined by Christine Graham, the product line manager for speed sensors at Allegro Microsystems. And Allegro has shipped over 1 billion of these sensors, so we're in for a treat today. Christine, thanks for being here. I'm excited for this.
Thank you. Thank you for having me.
So when I think about speed sensors, I'm thinking like optical counters or something like that. Can you give me a crash course into the world of speed sensing and what it takes to measure speeds?
Yeah. So speed sensing, you're right. Optical is something a lot of people think of. But speed sensors are they're based on magnetics from Allegro. And those magnetics, the one benefit is if you get a little dirt on the front of it, they're still going to work. The magnetic field comes through. The magnetic elements integrated with circuits, so you get compensation for the system. They can also be a bit more advanced than a pure optical, or in some cases a switch, a latch can be offered, but speed sensors come with more, let's say, brains behind them.
So like it says here, you can do some, intelligent sort of work. You can do some algorithm-based speed sensing and figure out your speed from those pulses. But let's ratchet down a little bit. Can you talk about front bias, back bias, and what are some of the advanced techniques people are using here?
Yeah, so speed sensors, like I said, they detect a magnetic field, and you'll see them detecting a magnetic encoder. So that's often called front biasing, okay, because the magnetic field is on the front of the IC. There's also, what we would call back biasing, which is when there's a magnet behind it and you're sensing a gear in front of it. Two different types of sensing for the sensor. And then, like I said, there's advanced processing algorithms that compensate for the IC, for that magnet that's included, whether it be front or back biased. And also application level, anomalies and perturbations you might see in the actual application.
So when might one use front biasing? When would one use back biasing? And what are kind of the advantages or disadvantages of each of those?
The front biasing is, I'll say, common if it's a cleaner application. It allows it. You're not picking up debris that might stick to the magnet on the front, because that can be more detrimental than sticking to the magnet when it's on the back. Gears are sometimes easier to use for that reason. And also in the applications that we're talking about, such as industrial, gears are more common because they're more robust. A magnet is soft. Think of a refrigerator magnet, right? You can take chips out of it and dig it. So various reasons. Cost-wise, they both can be expensive. They can both be cheap. It depends on how you want to design it, right? So it's usually performance and application driven.
So when it comes to sensing, we're sensing either rotating magnets or we're rotating a gear. Is the gear magnetic, or how does that magnetic sensing work, and what do those kind of signals actually look like?
No, the gear is not magnetic. If you're sensing a gear, we'd rather it not be magnetic because the magnet is back biasing the sensor now. Picture, I'll call it button magnet. So picture a little round magnet sitting behind the IC. Those magnetic fields now, I'll say, disturbed from the gear going by. So as you see a tooth or no tooth, it causes the magnetic field to concentrate across the IC. That's what you see when you see the magnetic signal. That's the concentration. Then the IC takes that, interprets it into an electrical signal, and then it's processed for the output protocol. That's really all it is it's just pure magnetics.
You basically run some edge detection on it, and you have yourself a nice, clean, processable signal.
That's right. That's the algorithms behind it.
So what are some situations where people are using magnetic sensors? What sorts of applications?
Oh, it's a wide range. Let's start with automotive. Everybody has, tens of them in your car. And I say tens. We've had quite a few in the past. Your transmission may have up to 4. Your crank will have 1. Your camshaft sensing will have 1 to 6, you know what I mean, type numbers. Wheel speed, your wheel speed is magnetic speed sensors. You'll have 1 on each wheel. So there's numerous uses. When you work into industrial, think of motorcycles, tractors, UTVs. They're all very similar to a car. They have those same applications. And then you have forklifts, right, where you might have a motor that needs very accurate, detection of that motor speed. Yeah. So various applications in both industrial as well as automotive.
Can you talk a little bit about temperature changing? This is one that I kind of struggled with conceptualizing as I was, doing some research ahead of time. How does a magnetic sensor help measure the changes in temperature?
Yeah, so you get temperature changes both from the IC heating up as well as the ambient air heating up, okay? The algorithms within the chip for speed sensing, they track that variation. So what they'll do is as the magnetic signal that's being interpreted into electrical starts to drift, think of it like an offset, right? So it starts at 0, it starts to drift up to 1, up to 2, up to 3. What happens is the algorithms can say, okay, I'm going to track that signal and then set my thresholds on it. So we call that dynamic tracking.
Okay. Because I kind of had, maybe in my brain, I didn't realize it until now, assumed there was some sort of AC coupling happening in the signal just so you could measure pulse width or duty cycle or frequency, but you're actually looking at the DC bias.
Well, let's go back 20 years. It would have been AC coupled. Okay, so that was a very common way to do it early on in speed sensing. Today, we have digital logic, right? We have circuits, ADCs. What they do is they can translate that from an analog to a digital signal. Then you're digitally tracking the signal. And when you do that, you can track the peaks. But then what happens is you could either do what we call peak detection or threshold detection, okay? So you'll track the peaks or you'll track the center of the signal. And that way, depending on the algorithm you want, the application you're designing for, you'll set your thresholds based on that digital tracking of it. So a little more complicated today, gone from AC coupled to using digital tracking today of the signals.
Okay. Yeah, it's not cost prohibitive anymore, I guess, to
no, matter of fact, it's better to be digital because, the way the nodes work and the process is, you can shrink your digital down to, as we all hear, right, nanometers, all these small dimensions, where if you're using the old analog discrete circuitry, you can't shrink those. Those are more physics. The size, it's difficult to shrink them.
That makes sense. When it comes to peak detection, is that where the air gap change sorts of measurements come in, where you're looking for an unusually high or low spike?
Correct. Peak detection is really, if you picture that, sine wave, and the positive and negative peak of that sine wave, it's where are those peaks living? And that's why another benefit of digital, with the analog tracking, you kind of hit the rail, it starts to clip, it becomes a problem. With digital tracking, you don't really care where it lives within the range. You're just tracking it full range, and you're digital, and then setting, your thresholds, your accuracy is dependent on it. Yeah, because the algorithms can also do additional calibration of that signal.
I also see an application here for sensor installation tolerance. Can you tell me more about what that sort of application looks like?
Every application has a tolerance. Right? We want to think that you'll build your system to perfection, but you don't. The sensor, think of it, let's take a gear tooth because it's easier. Not many people know magnetics, right? So I can't say a lot of people will picture that magnetic encoder in their brain. So I'm going to stick with a gear. A gear has teeth on it. We call it teeth, right? It's the actual gear teeth. So if your sensor isn't perfectly aligned with that center axis of the gear, let's say it's tangentially shifted one way or the other, that creates an offset. When you're designing, you have to account for that. That adds error, right? And that's part of the benefit of speed. If you're using something simple, a switch or a latch where it's got fixed thresholds, no algorithms, that shift can cause inaccuracies that do not get compensated. These sensors, they compensate. We talked about the temperature drift, but they also shift the baseline, in electronics, we all understand offset, right? So it'll have an offset that has to be adjusted. It may impact your amplitude of that sine wave, the peak to peak. All of that can be compensated so that your output accuracy stays consistent.
So I have to imagine, especially with backbiasing signals, distances make a difference, and the input signals can kind of look different depending on the situation. How do you handle those different types of inputs to get a consistent output?
Backbias compatibility, when you talk about front bias sensing a magnetic encoder, it can also have the same issues, but when you're talking back bias and trying to sense that compatibility, that's where a lot more complexity comes in with speed sensors. And that's where the algorithms have to play well with the magnets, because what you're looking for is, compensating. Again, we talked about offset. When that offset shifts, you can see the image on the far left here. It brings it down to a reference point. Let's call it the 0 point. And that variation is minimized. We don't show it here, but you can see the sine wave changing over ear gap, the largest being at that 0.5 millimeter, the smallest sine wave at the 5 millimeter. We also normalize that. So if you said, let me see the signal that's determining my actual output, it would be down around 0, and it would be a fixed, let's say, 0 to 1 amplitude. That doesn't change whether you're at a 0.5 millimeter or 5 millimeter. That's the compensation that's going on inside the speed sensors to give you that accurate performance.
So essentially, depending on distances, the signals can look very, very different, but you want to do the same processing on them regardless of what that input looks like. So you do some post-processing normalization to make them all usable.
That's right. And as a comparison, if you think of a switch with latch, it's got a fixed threshold. So as that sine wave goes up or down, what happens? Your slope changes, right? So your switch point changes, your output pulse width changes. That's all inaccuracies. So the speed sensors, they're based off the switch and latch in the old days. We talked about AC coupled, but they were also AC coupled, fixed threshold. We've grown over the decades, and now we know to compensate it so that we get much higher accuracy out of the sensor.
So clearly these are getting more advanced. What sorts of advanced tricks and techniques are being used? What sort of extra information do we get out of these sensors today that we maybe didn't used to get?
That's a good question. So more information. It used to be, I'll say, just a speed signal. So the output, that sine wave translated into a square wave. That was it. You did what we call edge detection on it. The rising edge, the falling edge. Very simple. We all think of electronics 101, right? It was literally that simple. Today, the applications, whether it be, sensing the speed of a wheel or the speed and direction of a motor gear, you have to now know forward direction, reverse direction. You can see that in the, plots where you'll have one pulse width that says I'm going forward, another one I'm going reverse. And then you can have options for what we call non-direction. So when you have anomalies in the application, such as vibration, you might see a forward, reverse, or some random of that. We can tell you, no, don't believe it. That direction, it's not legit, and therefore it'll give you a fixed pulse width. Again, that's different from the forward or reverse. So, and another example is you can get higher resolution. So it used to be the resolution was whatever the gear was. You had to change the gear if you wanted higher resolution or lower resolution. We can now do that from the chip, right? We can give you higher resolution. Two reasons for that. It can be either for accuracy, right? If you're doing displacement, more data gives you better resolution, right? Or you can say, I want a cheaper target. I don't want that 90-tooth gear. It's large, it's heavy, it's expensive. I want a 45-tooth gear. Well, okay, we can do a 2x resolution, which is sensing a 45 but giving you 90 pulses still. So it gives you the same resolution on a lower cost target.
How would you go about doing that 2x resolution? What does that look like technically?
Think of it, and again, feeding off switch and latch in the old days. Well, we also have linear, sensors, right? Linear and angle. It's more angle sensing, right? So now we're saying, okay, we know the magnetics. It's just how do you interpret them? So you can take a single angle, two angle, three, four, usually, let's think digital world. Okay, let's be honest. You got to do like 0, 2, 4, 6, 8, right? You can count
Yeah.
like that. And we can take those different points off that magnetic signal and give you the readout of it. You don't have to have gear teeth telling us, all the information. We can do some interpretive output based on the magnetics.
So going back to the direction for a moment, I never really thought about how important that might be, but I think about my e-mountain bike. Like if I'm rolling backwards, I don't want it to think I'm going forwards and try to provide some juice. That could be, both unsafe for me and also cause mechanical damage. Who is using these sorts of things now? Who cares about these sorts of advanced capabilities and features?
A lot of that it can be an application where you're sensing a motor and the reverse is important to know because, it can cause mechanical damage. Some of it is safety. Think about, motorcycles, for instance. You're seeing them require ABS now. Some of that, is a safety concern. So you want to sense the direction of the wheel. Is your wheel slipping? Are you rolling backwards? It also gives them the additional information they need to detect forward, reverse. Automotive has used it for years, right? For the same reason. They need to know when a car is going in reverse or forward. Same with most. It's either due to mechanical damage or safety of the driver. And when you think about two-wheelers, these sensors and their algorithms, sensing forward, reverse, vibration, slippage. It also, I know two-wheeler, some motorcycle drivers won't want to hear this, but it'll prevent them from doing pop wheelies. The things they shouldn't be doing because it can be very dangerous. So they also require it for the safety of not only them, but the people around them.
I'm not a motorcycle rider myself, but I think I only want to pop wheelies when I actually want to pop wheelies and not like on accident.
On accident, right? That's right. Exactly. Yeah. So the slippage there is important too, to know that you're going in the right direction, that your wheel's not doing something than anticipated. And it could be a mechanical failure too, right? I mean, some of these sensors can tell you, hey, it might be an IC failure, it'll tell you that, but then it'll also, the information going into their controller unit can say, wait a minute, my front wheel's doing one thing, my rear wheel's doing another. What's going on? And then they respond accordingly.
So as these get put into things like motorcycles, and we'll look at some more applications in a moment, what sort of form factor are these coming in? Are they integrated into larger systems? Are they kind of standalone devices? What does that look like?
Yeah, so the speed sensor, typically, it's not hermetically sealed. So you'll see the Allegro sensors, and they look a little different. If it's just an IC and you're front biasing it for magnetic coders, you'll see just a little square package that's just got the chip in there. And then you'll see larger packages that you can tell there's a magnet behind it. That's the back bias, so the gear tooth sensing. We sell both. If they want front bias, we have those ICs. If you are sensing a gear, we have them with the magnet. We do that for ease of design in, right? It's that way the magnet is optimized to the IC already for you. And they're not, but then they get overmolded. A lot of the time they're overmolded and there might be what we call a harness included, right? If you went into the motorcycle or your car and you pulled the sensor out, you'll notice there might be a 18-inch kind of pigtail on it. That's the further processing that our customers do. So we sell to a customer, they will do what we call a finished sensor, overmold, harness, and then that gets plugged into the application. And that should be more or less hermetically sealed so that the inside integrated circuit isn't getting wet. We're talking wheel speed sensors, right, in some cases. So they're down on the road, there's splash. There's some protection.
So what you're saying is you'll take the, Allegro chip and you'll often see that molded and combined into a larger system that then connects up and they can kind of provide their own amount of sealing and robustness.
Exactly.
Depending on the application it's going into?
That's right. And in some cases, they've asked us to take a portion of that. So we've put discrete components, let's say, in there, or EMC on chip. So when you're talking electromagnetic compatibility, which is the transients, the things you see in a line, that may also be incorporated into our IC. But overall, our IC is not meant to go directly into the application. It's meant to be overmolded and attached to an additional harness that plugs into the controller units in the vehicles, motorcycles, the tractor.
Wonderful. Yeah, that makes sense. You don't want to just like super glue it to your chassis.
No, not a good idea.
Okay.
Yes, they require specific connectors, and there's a lot of standards around that. So yeah.
And Allegro has been in the world of automotive and sensor technology for a long time. I have to imagine it's been quite the experience to watch the rise of sensing in everything. Can you tell me a little more, especially like in this motorcycle application, what sorts of sensors are we seeing today? Some magnetic, some otherwise, and also maybe share a little bit of like what's it been like to watch that rise of sensing technology?
Well, that's the thing. And in motorcycles, it's a good example because there's various types of sensors. Now, you might have seen them in the older days. I'll say, let's go back only a couple of predecessors to variable reluctance or inductive sensors, right? Variable reluctance, what we call VR sensors, started out being used. The air gap between our chip, our sensor, and that gear we talk about had to be relatively close. Through really in the last 20 plus years, we've really made so many advancements with electronics that those evolved into, the ICs that we develop today. They're not wire-wound variable reluctance type sensors. So that's pretty cool. But the other thing, when you talk about the technology, the motorcycle itself has evolved. When you talk about a motorcycle, they were more mechanical. The odometers were mechanical, right? Now today, they're much like a vehicle that you're driving, a light passenger vehicle. They've got the engine. They've got, like I said, ABS is now being mandated for safety. You've got a crankshaft, a transmission. These are very similar terminology that we hear in our car, right? So, the sensors have evolved with the application in automotive, as well as when you're talking about motorcycles. Motorcycles went from very simple mechanical, vehicles to highly electronic, using the same high tech that you see in cars today. That's been interesting to see not only the electrical advancement, but the safety advancement of the motorcycle itself in the fuel economy, right? I mean, let's be honest, people drive them to save gas. So yeah, it gets them down as well. Yeah.
But yes.
Yeah.
Yes, but also fuel. We've also seen a rise in sensing and integrated sensing in a ton of other applications. Can you talk a little bit about like industrial and maybe tractors, for example?
We talked about electrification, right? That has not stopped. Everything's becoming electrified, right? I mean, electrification is common, including in the industrial market, whether it be a snowmobile or a tractor. So the more common ones are like tractors, where you can compare it to what we all know. It's going to have an engine. It's going to have wheel speed sensors, right? They're driving through mud. They want to know if they're slipping. They might have chains on, but am I slipping? Am I going backwards? Am I going forward? Transmission, sensing. So you're still looking for that performance, the robustness of the vehicle. Breaking down out, 100 acres out in the field isn't fun. Yeah, so you'll see the same technology, the same electrification coming in. And again, a lot of these started with simpler, switch latch or variable reluctance, all the way up through now the smart speed sensors that we see today.
So if someone's looking to integrate these sensors into their systems, can you give us kind of a breakdown of the Allegro product line and what they might think about?
Yeah, so Allegro has a really broad product line. I mean, we've sold magnetic speed sensors for 30 years now, right? So there's a broad product line. Some of the newer ones we're seeing being used, you'll see speed-only sensors, the speed and direction. Some are, I'll say 3-wire, or what you might know as open collector or open drain. And then 2-wire, that's just what it's called, 2-wire, right? So it's just got a current source output. It depends on the application. For instance, Allegro is very commonly selling a product, the A1468, the ATS468. That's very common in the motorcycle applications. There's also more advanced, right? That one's got some algorithms. Depends on if you want to go even further into the algorithm, more advanced performance. You've got a product like the ATS627. That one can compensate, including for magnetic spikes around let's say if you have a crank sensor with a signature tooth on there, meaning it's got a coded target, that type of sense target, you might need even more advanced sensors. And then the wheel speed sensors. We sell wheel speed sensors. The 19200 is the most common one today. And then we talk about other industrial applications like the motor, type applications, forklifts, go up and down, automation. And that's where you'll find like a 17501, 502. That used to be 2 speed sensors, and we've integrated it into a single speed sensor today in order to help them, with placement within their application, with the accuracy, with the cost.
I'm curious, what's the most surprising or unique application you've seen someone use these sensors for? Like, I never thought I'd see that in this thing.
Probably a pinball machine.
A pinball. Interesting.
Yeah.
Okay.
We had a pinball, not the highest runner. But you do see, I'll say, niche applications. They're very interesting. We love it when we see, these high-end sports cars. They're cool. They're not, I wouldn't say they're surprising because they're cars, but high-end sports cars or racing motorcycles, those get the engineers most excited, right? They want to know if they can go test drive one. But but unique is probably pinball. We did have a pinball machine application, but we're also in applications like the trains, right? You think about a train, a subway system, they all use it. That's the thing. There's no limitation. We call these speed sensors, they're not really sensing just speed. It's speed, direction, displacement, right? And so it's got many uses, even though the name kind of almost puts it into a specific mindset, right? But they've got a wide range of application.
Well, this has been great. Thank you so much for your time today.
Well, thank you so much for having me.
That was Christine Graham from Allegro Microsystems. To find out more about these sensors or get some for your next design, go to thismauser.com webpage. I'm Daniel Bogdanoff. Thanks for tuning in to this Tech Chat sponsored by Mauser Electronics. I'll see you next time.